Dr. Veronica. Dr. Hessel is the co-founder of Genome Project, right? Which explores how to build a genome from scratch. And he's also the co-founder of Humane Genomics Incorporated, which is working on personalized cancer therapy. Their website says they're kind of stealth. So I don't really have much more information on that. Over our talk, we're going to be drawing on Dr. Hessel's experiences to talk about, one, the future directions of biomodeling, specifically from a synthetic biology perspective. Two, how we can work on achieving an integrated workflow for a whole genome design. And three, how biomodels can be better constructed to enable rational bioengineering. So let's give the floor to Dr. Hessel.
Terrific. And to share screen, I just press the screen button down here. Is that correct? Let's.
Makes sense.
It says host is disabled screen sharing.
Oh.
So attendee screen sharing. So if you want to see a presentation, we'll have to correct that. Nothing.
Huh. Sorry, 1 second.
Yeah. Oh, there we go. Perfect. So let me just fire up this. Now, can you guys let's see here. Does that work? Can you guys see the screen right now?
No.
No.
Nope. Okay, give me a sec. Sorry for this. Whoop.
No worries.
It's always, yeah, open system preferences. Yeah, this should be all right. Zoom. Okay, perfect. Hang on just a sec. And that should be okay. Okay. Okay, that says it should be sharing.
Yeah, it's good.
Great. So let me just start the presentation here. So you can see this okay? GP Wright and the Future of Engineering Living Organisms, a personal perspective. First of all, one small correction. I am not a doctor. My background is one of the strangest career paths in science I've ever seen. And I actually left my doctoral program and joined a pharmaceutical company quite early on. So I don't want to overstate my qualifications. Right now, I'm the CEO of a company, a startup called Humane Genomics. I'm working and exploring to do drug development as a service. My background is has been, as I said, pretty varied, but my core training is in cellular, molecular, and microbial biology and bacterial genomics. And I'm pretty much interested in the future of everything related to life technologies. Work-wise, I'm fairly independent. I tend to work as a futurist and a catalyst. And what I mean by catalyst is I put people together in a room and often excite them, inspire them, and challenge them to go do something new, often on spec and mainly passion-driven, because usually when you're trying this crazy stuff, there's no financial backing behind it. Professionally, I started getting really interested in kind of biomodeling back in 1995 when I was an author on a paper, The Genetic Map of Salmonella typhimurium. It was one of the first transitions away from the genetic mapping that had been done for so long and moving into physical maps kind of grounded in DNA sequence. And this just really got me excited that we could start to catalog and digitize entire organisms. And shortly after this paper was published, I had the opportunity to join Amgen, which is still one of the largest biopharmaceutical companies out there. At the time, it was larger than even Genentech, and it completely distorted my view of doing science, because we were printing money back then. It was really quite remarkable. Since then, since the Amgen days, I left in 2003, I became independent, and I just started moving around the world, taking a look at the emerging field of synthetic biology as it was booting up, meeting some of the players, helping out as I could. I was an ambassador to the iGEM program, etc. And I ended up joining a group called Singularity University, which is kind of the alpha geeks of Silicon Valley coming together to think about a future and create a school. It was really fun in the early days because it was a startup university, kind of no legacy. And it gave me a really interesting platform to go and kind of imagine the future of biology. Autodesk was one of the founding sponsors of Singularity University. And I got to know those folks really from the top down, the CEO and CTO. And in one of the engagements that I had with them quite early on, I asked them, well, you guys make design tools for, for building large, complex things like buildings and cars, airplanes. Do you have any interest in building design tools for living and molecular systems? And that set off a chain reaction of some diligence within the company. And in 2012, they formed a bio-nano group that they invited me to join. And it made me very happy, because I figured with Autodesk kind of bringing their resources to bear on kind of the modeling of life science, we might finally get, we might finally have a platform to start building together. Unfortunately, it was just a little early. I started introducing Autodesk to groups like Peter Karp's Biopsych and the databases of metabolism, just because so much work's been done to kind of collect this information. I'd also had some experience with a project called CyberCell, which was trying to digitize E. coli in the early noughts. They had about a $20 million grant. They burned through it pretty fast and really didn't get that much done, because 20 million in the biomodeling world just doesn't go that far. But it was a really ambitious project that I liked. And more than anything, I was inspired by Google Earth, because here is, it just gets more and more beautiful as researchers and scientists and organizations around the world start adding information to this platform. And I had gone to Google as far back as 2007 and asked them if they would be interested in kind of exploring Google Cell. And there was interest, but not a lot of motivation at the time. They said, well, if you can get people together, you're welcome to play with the platforms. Autodesk, for the most part, wasn't that successful. I wasn't able to really motivate a large group to kind of start thinking about biomodeling and biodesign as much as I would have liked. It's just not in their DNA yet. I was the first biologist they'd hired, and they really needed to form a core group. But a couple of really good things came out of it. One of them was I had the opportunity to catalyze something called the Genome Project, right, which is ostensibly the follow-up project building on the Human Genome Project, which was about reading our DNA. We were starting to think about, well, our genome design tools and our DNA synthesizers, they're starting to get a little better. We should really start thinking about writing whole genomes. And frankly, the only genome that most people care about is the human genome. It's not a scientific observation. It's really just an observation of what people are interested. We tend to really be, don't extend our views too much beyond ourselves. It caused a lot of controversy at the beginning, but it definitely got attention kind of directed at synthetic biology, and it's grown fairly well, considering it doesn't have a lot of resources. We have about 1,000 people connected to the project now, about 200 scientists, about 100 institutions, and it's still not really I'd say that it's still not really working in a very dynamic way because it's still early days, but we know that if we just keep moving forward, this is going to become more and more relevant. Certainly the news out of Hong Kong about gene-edited babies really starts to put the frameworks that we have in the Genome Project right, and the working groups, which include society and ethics and technology and law and standards, et cetera, really brings it to the forefront that we have to start thinking globally about how we are going to start engineering the world around, the living world around us. I personally think that as the Genome Project right continues to evolve, it'll end up looking a lot like OpenAI. OpenAI was actually founded about the same time as the Genome Project right, but it had the benefit of having $1 billion pledged to it by some of the founders, and so they were able to build a core scientific team and start doing some really state-of-the-art research that they can share, plus build tools. So what we're hoping for now with the Genome Project right, as it starts to solidify more over the next few years, is that we'll get one of those big philanthropic backers or a large government grant coming in from one of the organizations to basically put some funding behind it. But right now it operates as a federation of laboratories. And George Church, one of the principals, has estimated that several $100 million has flowed into this federation in part because of their collaboration with the Genome Project, right? So I look at it as fairly successful. The other thing that I've been involved with at my time at Autodesk was I started getting really interested in synthetic viruses. Now, this has been a passion of mine for a long time, but I recognize from a modeling perspective, the virus was probably where Autodesk needed to start, because a virus is non-metabolizing. You can basically look at it as a piece of molecular furniture, and without having that dynamic system, it made it pretty easy to start to think about how we'd model it and be able to use some of our existing modeling tools for visualization and simulation. But I also want to take them into the real world of biology. So I started doing genome synthesis of viruses, Phi-X174 being the first one we synthesized, and then worked with Paul Jaschke, who was then at Stanford, to do the boot up procedures of the virus. So this actually really caught the public's attention in some ways, certainly the tech world's attention, that Autodesk, a software company, was now making essentially biological software too as part of their prototyping. So that, I look at that as a success, and it's actually formed the basis of my startup, Humane Genomics. I'm out of Autodesk now, but I took all the virus work with me, and for the last, we've been synthesizing adenovirus from scratch and making it oncolytic using a recombinant virus that had been developed several years ago as our initial template. And now that's been sent off for publication, but we essentially have prototyped a platform that allows us to do design of a virus to treat a single dog. And it's a pretty straightforward procedure. You get a biopsy. We're currently doing osteosarcoma. That biopsy, you can do molecular analysis on it. We find the transcriptome is pretty sufficient. From there, we can use CAD tools. They're not very sophisticated today, but we certainly want to start focusing our efforts on building better CAD for these nanoparticles. And then there's plenty of facilities today that will synthesize whole genomes and do contract lab work to boot it up. And then testing is still a pretty significant bottleneck. But just starting to do this iterative design, build, test with viruses has a lot of economic potential, research potential. And it turns out the field is still pretty young. The first synthetic virus was made in 2002. There's been less than 30 synthetic viruses made since then, which really speaks to how anemic synthetic biology is today. But I would love to be able to get to you know, to the point where we have really accurate molecular visualizations, plus the dynamic engagement, being able to go out and pull out a puzzle, you know, a protein piece of the capsid, for example, pull it apart, examine it right down to the atomic level, and then potentially do tweaks, et cetera, resynthesize, reboot, get the data. I'd love for this type of engagement to go faster. And just last month, I pulled together a group of folks along with ASU's Biodesign Institute to really explore how we might put a broad academic foundation under the field of designer viruses and nanoparticles. And this was really, I think this type of foundation is long overdue. But I think that the timing is getting pretty good, because the tools that we have for designing and building certainly viruses and nanoparticles from scratch are sufficiently robust now that pretty much the entire viral world is open to us. So I think this will be pretty interesting. So right now, ASU is looking as a front runner for establishing a center in this type of area. Really, I'll stay tuned to see what happens. They're just taking that to the president now, I understand. But that's a pretty big leap. Okay, moving on from viruses, another really a success, I think, that came out of my time at Autodesk was I learned about a project that had been spun out a few years earlier called the Parametric Human project. And this was a scientist by the name of Azam Khan, who really had a deep interest in modeling the entire human. And he started working and putting together a group of different research institutions to kind of start putting data onto this model. So, you know, they really believe that creating a centralized data repository, you know, really can help advance things like healthcare and design, biological design and wellness. So I really loved this project, found out that it was basically brand new, and volunteered to be their first human guinea pig. So I had been completely scanned by the project using a rig, something like this. It's the same rig they use for actors and digitizing them for movies. It's really quite a remarkable data set. They stuck me in an MRI and scanned me head to toe for an afternoon. And I even donated my full genome to the project. So I'm essentially trying to make myself into a digital avatar. I think this is going to be a lot more common in the future, but right now it really takes a lot of effort to go and build these models and have a platform for doing it. But we were lucky enough that George Church is now the second parametric human, so we'll definitely leverage him and his assets to keep doing, driving this type of work forward. I really just want to give some future perspectives, because again, I don't do biomodeling. I just love biomodeling because in my head, I have this ability to empathize with molecules. Like I often find that I can sit on top of an enzyme and ride it like I was riding a motorcycle. So it makes it very exciting for me to think about molecular systems, but I realize most people just aren't there. A year ago, when SpaceX launched Falcon Heavy, just before they launched it, they released this animation that I just caught my attention, just because one, it was, if you watch the whole animation, it's really remarkable the detail they have in kind of mapping the entire mission in a digital way, in a digital fashion. It's really worth watching the video. But one of the thing that caught me about the animation was it showed the boosters coming down side by side. And I was hooked. After that, I just needed to watch that entire process, and it turned out that that's really, that's what they were able to accomplish in real life. So this was a really powerful example for me of being able to kind of map a whole experiment digitally, have a really good understanding of all the physics, show people what it's supposed to do, and then go and actually create it in the real world almost precisely. And I thought, wow, like, that is so cool. And not to mention they had fun. You know, launching a Tesla into space was just fun. Like, man, sometimes it strikes me that biologists are just so serious. But clearly the engineers are moving beyond that. And then I've got some really good friends that started a company called Planet. And this is interesting because this is a rack of satellites. These guys launch more satellites than any other organization in the world because their satellites are essentially, microsats. And so they have hundreds of these satellites called doves currently orbiting the Earth. And the way it works is it essentially sets up a ring and the Earth rotates underneath it, and they digitize the entire planet on a daily basis, all the land masses. And it all feeds into kind of Google's architecture for doing object recognition. Which is kind of cool. And that entire pipeline is pretty remarkable, and anyone can go and sign up at Planet and start to explore the world in 4D, not because you can look at any point on Earth, but you can slide back and forth in time, and it's pretty stunning. And I was hanging out with these folks last year and just learning about their data pipe, because I just think it would be so cool if we could be doing that sort of thing with cell biology. You know, in short, I think it's really on the biomodeling community, you know, to make exploring inner space as exciting as exploring outer space, and to be able to understand the physics and the biophysics well enough that we can actually start doing this in a way that is realistic and supports experimentation. There's a lot of trends right now that are really starting to fuel life science in a way I've never seen before. And this is one that I've been speaking about for the last few years because it's happening now. Genomic networks are on the cusp of a massive, massive growth spurt. And that's because we've had the genome now since 2003. And the cost of a genome has just plummeted. You know, today to, George Church was saying recently, all in a whole genome sequencing is about $300 now. But what's been happening, so we've had this incredible price reduction, but we haven't really seen widespread adoption of human genome sequencing just because it's still been under the radar. It's hard to articulate the value of a genome, but the green line on this graph shows kind of the growing value that we're learning how to extract out of human genome data. And recently we crossed this economic inflection point where for just about anyone on the planet, you can get more economic value out of their genome than the cost of acquiring their whole genome. So we're on the start of a genomics explosion now, because once it becomes economically exothermic, you're just going to get a ton of genomes. So that's happening now, and it's only going to keep growing. This is important because suddenly we have more human genome data coming into the databases than we've ever had before. It's going to be limited in the short term because right now our sequencers we just don't have enough sequencing capacity to do tens of millions of whole genomes, but that'll ramp up. This is a company that will be part of that ramp up if I'm reading the tea leaves right. It's called Roswell Bio Technologies. We know that Illumina is kind of the big daddy in sequencing. We have other companies like Oxford Nanopore that have a competing technology. Roswell is the first example of where you don't have a pore anymore. You just have the polymerase enzymes doing its sequencing reactions, and you just read the enzyme dynamics directly on the chip. It's basically a sensor array for polymerases. So this promises to do human genomes in minutes for very, very low cost because it's just all semiconductor technology. We're also starting to see smart growth chambers. This is a smart petri dish developed at Georgia Tech by a researcher named Hua Wang. It's remarkable because it has electronic sensors for the cells. It has optical sensors. It has and there's even other ones. There's the full specs are out there, but this is fascinating to me because now we're just starting to get the ability to interrogate and monitor cells non-destructively, which I think is really going to be an important part of the feedback loop in any biomodeling we do. So this is pretty exciting. This is new technology. It's just being they're trying to commercialize it now, but this is going to be really important for doing things like drug screening. And then in my world, the most exciting kind of shift that's happening is we're moving from chemical synthesis of DNA to enzymatic synthesis of DNA. And I think this is going to be transformative because when we get these kind of the molecular electronics working correctly in this field, we're going to be able to make genomes pretty much effortlessly. And it's hard for people to imagine today, but it's hard to imagine a $300 genome sequence compared to where we started 15 or 20 years ago. I'm pretty sure that we're going to have human genome scale synthesis appearing in the next 10 to 15 years. And that's because it's not that hard. Honestly, every time a cell in our body divides, it makes a human genome. We just have to tap into that equipment and learn how to direct it. This is important because now we're going to get a feedback loop into our models, whether it's E. coli, whether it's anything more complex. We're going to be able to design and build organisms a lot faster. And I certainly think the virus world is going to benefit from this probably before any, even the cell biology. And then we are starting to see, well-financed groups come into the world of kind of biomodeling cells. It's still not as engaging as I would like to see it. It's still not I don't know the details of whether this is an open platform, whether people can start to build on it. But my vision for the future has always been, let's really just build, the biological equivalent of Google Earth, but for a cell, and start letting people curate and add data and tune the physics so that it's representative. I think when that happens, we'll really start to see some more activity. But and this is from personal experience, but I think it really, the world of biomodeling opens up to in a whole new way when it starts becoming ported to AR and VR. And that's because the world that we work in molecular systems is invisible. It's just invisible. Most people cannot really imagine what that world's like, what the dynamics are like. And the diagrams in textbooks and papers just aren't sufficient. You really need to have engagement and activity and ways to manipulate. And if you haven't tried a good VR system, you're missing out, because it is transformative. It literally teleports you into that environment. And today, it's not as seamless as it should be. It's not as high resolution as it should be, but the experience itself can be breathtaking. And you see it all the time in demos where you have someone just walk a virtual plank, across a chasm, and they can barely walk across a straight line across the room. It is bizarre. Or the roller coaster demos that they had, people would get incredibly nauseous. So I think when we can start to go into these models and explore them as easily as we might explore real world objects, it's a game changer. And if you pick up this is the latest Wired, they're kind of starting to recognize that as well. This is kind of timely, but they just call it the mirror world, that essentially every environment, every object is going to have an AR, VR equivalent. And we're essentially digitizing the world around us. And I don't think that's limited to the macro scale. I think we're going to start to see these tools that are being developed for completely different purposes be used increasingly for doing this type of modeling at the cellular and subcellular level, as well as macroscopic systems. And I think it will just lead to a whole new generation of scientists, of industries, and kind of the supporters, recognizing the value of this work. And that's it for the presentation. So it's been a personal journey. It's still ongoing. I'd love to, at some point I'd love to learn more about how your community has been growing and thriving and evolving. But let's just say you're doing really important work, and I think it will become more and more recognized as it continues to advance.
All right, well, thank you, Dr. Hessel, so much for that talk. First off, can you stop sharing your screen?
Yeah, I can do that. There we go.
Yeah, so I guess first I'd like to invite, everyone here if they have any questions for you, or thoughts on sort of how like one thing you mentioned was like AR and VR, but like questions people might have about how biomodeling can sort of adapt to help integrate itself more into the synthetic biology community and science overall. So anyone have any questions for Dr. Hessel or thoughts?
And again, not Dr. Hessel, just Mr. Hessel is fine. Andrew.
Yeah, I was just curious if Andrew knew about the NIH project called HubMap. It seems to be just starting up.
I have not heard of that, Randy. Can you give me a brief overview?
It's hubmapconsortium.org. If there's a chat, I can drop it in there. But basically, you mentioned wanting to see a day of having Google Earth for the cell. And I think that's sort of their motto is, they're basically trying to map the entire human body, healthy body, and map it in different ways and bring it to the visual.
That's fantastic. I applaud any effort that takes us a step closer.
Thank you.
Yeah, so I have a question. I was wondering. I'm curious what so one group you mentioned is Google as like a potential community that would be interested in biomodeling. You think there are sort of any communities we should reach out to or applications who sort of would be interesting in what biomodeling can offer, but that isn't being pursued that much right now?
Well, I want to be clear. I think every group, all the big tech companies, Facebook, Google, Amazon, I think they're all very interested in the potentials of biomodeling and just biology in general. But I think they're just taking baby steps into that because it's not part of their core business. Certainly the new Chan Zuckerberg Institute is starting to bridge some of those gaps. Google's got an active life science investment group. It's just, for me, I think the biomodeling community needs to either have its own business model, which is unlikely in the short term, or to be partnered with a group that has the heavy-duty compute platforms that's needed to do the modeling and simulation. It's astounding to me how complex these models get because there's just so many moving parts. And we don't have a full understanding of the physics that these, of the biophysical environment yet. So I think that's a challenge, but we certainly have the capabilities now of starting to make these dynamic models working in real time. It's just that those types of computes are expensive. Autodesk had their own internal cloud, and just doing some of the very simple protein simulations tended to crash that cloud. So again, I don't have the technical expertise to really imagine this at scale, but I do believe that Google Earth is a great example where you can layer on more and more detailed information about one ball in space. And it has benefits to a much larger community. I'm pretty sure that even if it's a generic cell, will produce similar benefits in R&D.
I'd like to give us, hi, this is Arthur. Can I talk?
Yep.
I'd like to give a slightly different perspective on the challenges of building dynamical biomodels of a cell at scale. I work here with Jonathan Carr and the rest of our team at Sinai. And while I do think that long-term compute service of massive scale will be very important to our field, I think that shorter term, we're facing challenges that come before huge amounts of simulation. And they include aggregating data, developing tools and frameworks and formalisms for describing models, learning better how to verify and validate models. And those I expect are going to be the major challenges in this field for the next 5 to 10 years.
I can't disagree with you. You're on the front lines building, virtual cells. I think in some ways, I've always believed that if we can create the right platform and right framework, the scientific community will populate it. But right now, most let's just say there's a very low awareness of this type of work being done in general, and very low priority being put on it. I'd love to see that change. Like I think modeling the cell is equally, if not more important than modeling our planet. So anything we can do to raise awareness of all these issues and build and grow your community, I'd just love to see that happen. Right now we have stories to tell.
Well, thank you for your support.
I wish I was a billionaire. Still working on that one.
One of the challenges in funding our work is that it's extremely multidisciplinary. So it involves computer science, mathematics, biophysics, biochemistry, and so that whenever one approaches funding agencies, they only feel like they're responsible for funding part of it.
Yeah, there's no holistic view right now. It's this fragmentation that I think is starting to hold us back. It's very hard to, as a community of scientists, work together on any large collaboration. This is why I think that a digital cell could be a really good way to start growing the larger community. It's just overdue. It's something that will absolutely emerge in time. But, I just think that for the things that are important, the more we can do to grease the wheels, the better. And some of that, it just comes with raising awareness of the incredible work that you're doing.
We have a question from Hector Garcia Martin.
I can make it myself if you want to.
Oh,
So
yeah,
I
that'd be
was
fantastic.
wondering, where would you start to make it change, to actually bring awareness to the importance of modeling cells and being predictive about it? I would like to know your point of view. I have my own ideas, but I'd like to know what you think.
Well, it's actually the way I've been doing it, and I actually make my living at this now, surprisingly, I just go and tell stories about people doing what I think is really awesome work. And it'll change. I never do the same presentation twice, and I'm always meeting with different groups. But as I was saying just before we came online, I'm flying to New York tomorrow night to go and hang out with an exceptional group of individuals that just aren't exposed to biology at all. And I get to tell stories with them. And these are all, in positions of wealth or privilege or power in government, et cetera, et cetera. So just raising awareness is so important. Publishing papers in academic journals is great, but it doesn't have a broad reach. Like getting stories about the work that you're doing personally or as a group on television and in popular magazines really helps to just have people understand what you're doing and why you're doing it, and it inspires others to to shape their careers, to join you, or to, if that's not a possibility, to start writing checks, just so that they can have a little piece. I wish there was a way to just go and make a case that would provide you with sustained support at the level you really need, because I know it takes billions of dollars to coordinate any group of people to do anything these days. But let's face it, that's not coming top down anymore, at least in the US. It has to kind of grow bottom up, or it has to be a public-private partnership. So the more you can share the stories about what you're doing and what you consider to be your successes in popular channels, the better. It's not something scientists are trained to do, though. Like and the idea of self-promotion is just doesn't really go over well with most scientific communities, and I get it. That's why it's good to have friends that are journalists. It's good to have friends that make documentaries, that make podcasts. It's great to participate anytime anyone invites you to do any talk, seminar, training, etc. I just try and say yes to everything, hence why I'm here. Because I'm not qualified to understand the math. Like, that's not going to happen. But like I parse this stuff through what would I like for myself and my kids, and I want them to have a complete understanding of the cell and of their bodies and of the other creatures around them that they might get from, if they go and pull up the specifications on any electronic device. That's the difference between, the technologies we've developed as humans and these natural technologies. Nature didn't write instruction manuals. The code is spaghetti code. The physics are biophysics, which are, pretty much magic. But I'm doing another presentation for a group of private bankers tomorrow with about something like 23 billion under management. And I'm starting off my presentation with a quote from the dying Steve Jobs, where he recognized that one of the most important developments of that's emerging in this century is the intersection of biology and technology. And he said this is really the start of a new era, and I think he's right. Like, this is a really profound time, because we finally got the digital nervous system to start working together as global communities. We've got the computing architecture now to really aggregate massive amounts of data and process it, and now we also have the tools to start building biology. And even though this is very early days in the synthetic biology community, I guarantee that when that next generation synthesizer hits the market and becomes available, you're going to see a Cambrian explosion of microbes and viruses and companies being built on that foundation. And it's going to quickly advance up through the tree of life in terms of the complexity. And granted, most of it will be copying to start with, but you're going to see this diverse space be explored for positive applications, new wealth, et cetera, et cetera. So I think that biomodeling is going to become, is going to have a business foundation, an economic foundation that supports it, emerging pretty much over the next decade. And you should be prepared for that for that growth.
Okay, thanks.
Hi, I have a question. Is it okay if I talk?
Yeah, go.
Okay, great. My name is Yoshi. I'm from Seattle. I'm at a place called Sound Bio Lab. We're a DIY bio lab in Seattle. And I had a question specifically about, you mentioned bottom-up approaches. We really want to encourage other people, especially the common folk, who don't have a lot of biology experience and background to take in biology. And of particular that I find fascinating are programmers who are working at tech companies here. In terms of what you do at GP Wright or other initiatives that you're part of, how do you think that even people with no experience in biology can actually participate and contribute to these kind of initiatives?
That's a great question. And this is ancient history, but in 2008, I introduced Matt Cowell and Jason Bobe, who were the founders of DIY Bio. So I am a big supporter of bottom-up approaches in DIY Bio and these types of initiatives. It's great to see how much they've been flourishing. What I believe is as we start to build better modeling, design tools, etc., it really opens up the field of life science to a much more diverse community that don't necessarily need to have the deep training and all the aspects, the low-level stuff of biological systems. Just like to program a computer, you don't need to know semiconductor design. This is starting to happen. There's a company called Asimov that came out of Chris Voigt's lab, but that software allows electrical engineers to make biological circuits because it uses the same language, Verilog, that they're used to, and all of the compilation of the biological circuits done by the software. So I think that's kind of where the field is going to go. First of all, anyone can be a scientist. It's just if they have the right tools and the right culture. But already, you know, DIY Bio, as the sequencing world starts to open up, you know, it's a workforce. Go and pull any organism from anywhere, a swab from your toilet, the plant from your garden, the bug that you found crawling across, you know, your table, anywhere in the world. That's now, you know, essentially fodder for sequencing and analysis. Great. There's going to be a ton of business models, but as the design tools for programming metabolism, which are emerging now, they're still not fun, but they're reasonably good now, combined with next generation DNA synthesis, which, if I read the tea leaves right, will allow you to make a microbe like E. coli, you know, from scratch in a matter of minutes. And again, that's not here yet. It's going to emerge, but that will come. Then you're going to see people specializing in just metabolic programming. They might not have any biological experience, but once you start doing design build test of an organism's metabolism, and it's coupled to the testing cycles where you can actually go and verify that you're making the thing you're hoping to make, or the organism's doing the things it's supposed to be doing. Once you have that feedback loop, it just starts to accelerate. And since generating a whole microbe now that does something useful is worth billions of dollars potentially, just looking at the ginkgos and the zymergens, I think we're going to see the community, biodesign community, really start to flourish. And it's not going to be limited to just the academics. You know, in fact, if anything, the academy is kind of losing control of the genetic engineering and bioengineering story because it's just broadening so fast.
Great, thank you.
I love the image behind you, by the way.
So we have a question by Playman that says, do you think that mechanistic models will deliver the expected technological breakthrough for biosystem modeling? Or if anybody else has any insights into the type of underlying mathematics that they think might contribute to this breakthrough and wants to comment on that.
I'm not qualified to answer that one. I just have faith that the math works. If we can put up skyscrapers, you know, and model them. First of all, at Autodesk, they had generative design tools that were pretty amazing. You could just take a plot of land and basically parameters for a building. It can be so tall, it needs to hold so many people, they have to be able to get out of it in a fire in this many minutes, this is my budget, whatever. The tools were sufficiently good that it could auto-design the entire building. And that to me is remarkable. But when you think about it, the physics are all known. It's not as complicated as biophysics. All the parts and components of a building are known and have been modeled, and all the parameters put in a database. And just the constraints on the system is really just your evolutionary environment. And the computer software tools can make millions of models that satisfy those constraints in a few hours. And so the designers would just come in and say, I like that building more than the other one. And it doesn't have to be a building. It can be a chair. It can be essentially any object built from standardized parts with known physics. I really believe that's where cell engineering is going to go, and eventually organism engineering. And granted, I'm an optimist and a futurist, but it's not impossible. And you get inspired when you see the work that's being done in the large dead world.
So it's me again. You know, I was wondering, Andrew, if you could maybe tell us a little bit, you know, about why Autodesk decided to not work on the biological world anymore. I mean, what are the hurdles we are going through in order for making this happen? And what was your experience in Autodesk, and what were the main problems for them not to invest any further?
So I want to be clear. Autodesk is one of the finest companies I've ever worked with because they're kind of agnostic, and they help everybody make anything. So they're not tied to one particular industry. When I joined them, the CEO was a guy named Carl Bass. And the CTO was a fellow by the name of Jeff Kowalski. And these two were both brilliant and risk takers and very intuitive. You know, like they just really acted on their gut sense. And so when I asked them if they were interested in building, you know, design tool for biology, they did some homework, but then they committed resources to it. It got off to an odd start. I came in with a really clear focus, but the rest of the group, you know, not being biological in nature, kind of wanted to explore the space, and so they got a little lost for a while, and then they finally started to get some traction and put together some really good visualization tools and genetic constructor, et cetera. They really started to get ahead of steam up, but by this time, several years have gone by. There'd certainly been some challenges internally, but a new CEO came in and a new CTO, and they're currently very focused on their core business of architecture. They're really putting some efforts in to take that to the next level. So I can't fault them on their choices, but I still write the CEO frequently and say, I don't think you should drop life science because it's just going to be too integrated and too important with things like biomaterials. Generative design ends up producing objects that look very bioorganic. So there's a lot of cross there. They still make buildings for people, and you have to understand people and microbes if you really want to keep them healthy in buildings. So I think they'll come around to it again. It's just not core to their business now. But if you want to go and make an argument, that they should continue their work, I think they'd love to hear from you. And Andrew.adnagnost@autodesk.com is the guy to write to. and he's a really strategic guy. I think when he starts to understand the value for the business, they'll come back to it. But they're not the only ones. Like, let's face it, the Ginkgos, the Zymergens are all building their BioCADs. GP Wright hopefully will end up getting a platform of tools at some point to do that. And I think as we start to, again, for me, the bottleneck is the compiling of the code. You can design a bacterium today just by dragging and dropping a current genome. It's not a original design, but it's patentable if you change just a few base pairs. So there's a lot of motivation to do that. But to synthesize the genome today is just too expensive. And my speaking point on this is Craig Venter did the first synthetic bacterial genome in 2010, and the second one in 2016, but no one has done the second, or the third, synthetic bacterial genome. And that's globally, so clearly there's a big economic canyon between design and build right now. And that has to be bridged to really get this community going. And even with viruses, I think the adenovirus that we made is the second largest virus made. It would have been about $30,000 of synthesis if it hadn't been donated. Like that just has to change. So for me, I believe that will change soon, and that it'll just light a fire over all bioengineering, under all bioengineering, and really get this going.
Yeah, but you seem to think that the initial spark is going to come from the private sector, right?
I think so, because right now, I don't know how you guys are funded, but the private sector can raise $1 million faster than any scientist can get an R01. And you can spend that money faster on anything with less reporting. Yeah. So I think that I have nothing against academic science, like nothing. It's absolutely the bedrock of all achievement. But what I'm seeing now is that the overlap between R&D is getting greater and greater. A lot of researchers now have their own startup companies. They're supported by the universities to do this type of stuff. It's getting a little murky. But that being said, the fact that a researcher now can actually independently run a drug company, I think is kind of cool. Yeah. And it's certainly putting the developers, the development community on edge. They're starting to realize a lot of people are going to come chasing after their lunch.
Yeah, thanks.
You're welcome.
I'd like to ask one much broader question just before we end. So historically, all new technologies have been deployed by firms and governments for economic, political, and military advantage. So given this, Andrew, could you talk about your thinking about the societal consequences of synthetic genome engineering and how it might be regulated for the good of humanity?
Yeah, that's a great question. So I usually tell people that I am not qualified to do any type of ethical discussion. I'm not trained in anything like that, and trying to apply precautionary principles, etc. I'm just not good at it. Here's how I frame everything. Does the technology exist or not? Literally, can it be done? And if it can be done, if there's anything beneficial, if there's any desire to use it in any way, it's going to be used. And so, and it's going to be used in depending on the environment. It's either going to be a black market, it's going to be a gray market, there's just no regulations, or there's going to be a white market, it's going to be approved. I think that we're starting to see that we need to rethink all of our parameters around biodesign right now. The current regulatory agencies are just too slow, can't work in real time, can't deal with the complexity. I think that the issues are going to be borne out very quickly because of synthetic virus engineering. The recent National Academies report highlighting biosecurity threats puts designer viruses pretty much right up there at the top. I think that because the current tools and technology make that accessible, I think we have to start thinking all the frameworks on this. But in general, most people will work on a positive application. So it's the groups that are working in the dark that I don't know about that I'm more concerned about. And there are certainly a lot of motivations to go and do some things in the dark. I think this is why GP Write is important. I think that other organizations, if they do GP Write things, GP Write like things is important. Keep it open and transparent, shine the spotlight, share the understanding, and more than anything, monitor what's going on. I like open platforms like Linux because the way I always looked at it, if you're publishing the keys to the lock or the specifications for a lock, it must be really hard to pick. And you always have to be out looking for people trying to pick the lock. So I think that there's an opportunity for this community to come together to really, because we understand it the most, start looking for the weird behavior early and start trying to think about where we build next generation biodefense. Anyway, long-winded, don't want to use up any more of your time. I can talk at length.
All right, well, thank you so much, Andrew, for speaking to our group here. It was a very great talk and we really enjoyed it.
Well, thank you very much. Again, I think the work you're doing is so important, and I hope you always have lots of interesting intellectual challenges and plenty of supporters to keep you moving forward. Anyway,
Thank you.
Thanks again.